working on an operating system for future smart spaces, and his research vision is making pervasive computing become ordinary for people as mobile computing is today. Let's welcome Mark Oliver.
Thank you very much. Actually, in the back, you can just not see, there's a picture of the university building, so there are huge slides. So whenever you come to Munich and go to university, I recommend you go there, because there you can slide down from the 3rd floor to the ground floor, and this is quite fun. Okay, so as you said, I'm working on operating system for smart spaces, and this is the illustration belonging to it. So you probably all have smartphones, and the great thing about a smartphone is you can just download a new app, and then you have new functionality. So you can make pictures, you can record things, whatever. And to me, it's a great thing if you could do the same for physical spaces like this room here, so that we could download an app and install it in our smart space. So what is a smart space? So a smart space is a physical space that contains cyber-physical systems. So systems that connect the physicality, so our surrounding here, with software. So that we can use the software to control things, like switching the lamps here, closing, opening the shutters, opening, closing the windows, and many more things. So the more sensors and actuators we have deployed, the more things we can do. In this area, there are many challenges, because what is currently missing is kind of an operating system for such spaces. And I'm working for several years on such a thing, so the bottom layer here is such an operating system. I will detail a little bit more my approach here. And on top of that, you have the usual things that you need when you want to have an app economy. So you need some sort of app store, you want to deploy apps, and you also need different kinds of apps. So you need user interfaces, you need software that enriches data, so this is called reasoning, or you need software that connects different of these devices with the operating system. And what is especially interesting to us today, what I want to look at, is when you have such an app, what you do is you connect the different sensors and actuators to it. And so how could deep learning now come in here? I will show you. So this is the operating system that I'm creating for the past, I guess it's now 8 years. And what I basically do is, you have the physical surrounding, so this is the dark layer here. Then you have hardware devices, so sensors and actuators or smartphones that interface between the physicality and the cyber. And then you have software processes. And then, as highest level of abstraction, you just have data. And this data is called context in the pervasive computing, ubiquitous computing area where I'm working. And this context is structured. So here you just see a simple XML representation. So basically what I do is I do a hierarchical representation. So you have a device, and the device has different nodes, and the different nodes represent the different properties of an entity. So like when you have a heater, it could have current temperature and current inflow, outflow, and something like that. Okay, so this is important to take. So we have the reality, and I transfer somehow the reality to this structured data layer. What you can do then on this layer is you can make a service-oriented architecture or also modularization. So that means you can take complex functions and you can decompose it into different parts, and you can recombine them to create new complex application from smaller parts. Okay. And this here is so-called virtual state, and now we come closer to the deep learning, because you can also represent this virtual state just as state vectors. So you can assume, so this here would be one entity, so it would be your flat, for instance. And so you can assume that you can model the entire flat as a state vector, so this would be then an entire space. You can also model a service as a state vector, because even though this is hierarchically structured, you can also just see it as key value pairs, where you have different values and they are in some kind of a vector. Or you can have processes that go over multiple services, but they are still a vector. And what happens basically is, software is running, and the software is either taking something in from the outside, so from the physical space, like the temperature changes or other events, or software is changing its state because it's reasoning and then it's getting later in the day and it assumes, okay, now it's getting night, and then it's storing, okay, now this vector entry is currently night. And so what you have then is you have a development of those state vectors over time. Okay, and such state vectors is something that you can put into a deep learning network where you can learn something and where you can do something with the data. And actually, the possibilities on what you can do are more or less limited only by your imagination, because today you can build almost any hardware that you want to build. Because you have do-it-yourself hardware like Arduino, Galileo, you might have heard about it, Raspberry Pi, so you can create any hardware device that you want, more or less. And one application where such learning is applied already, because in my field it's not applied very much. So one application where it's applied is activity classification. So in the background you see an office space, and then you can have movement detectors. And the output of those movement detectors you can put into a neural network, and then the network can learn, okay, this is a working situation, this is a cleaning situation, and maybe someone is trying to break into my space. And then you would have this data, so this will be a reasoner, and then you could do something with it. Okay. So, to sum it up again, so we have physical phenomena, then somehow we extract this state, so this context data, and then we can have software applications, and they can do analytics and also orchestration, which means that they do something. Like they open the window, or if you think further, you could have a robot that starts interacting with you with all the implications that brings. And so what you can do then is you can use the deep learning as an important aspect for creating artificial intelligence. So yesterday we heard in the opening ceremony already about this HAL computer, and so this is exactly a screenshot from the famous movie Odyssey 2001 from Stanley Kubrick, and the other one is from Star Trek. You might also know that one. And what I simply want to show with that is that in these cyber-physical systems where you transfer then the physical state so that it's processable by software, you have then all possibilities. So I typically compare computer science with magic, because basically when you write a program and you're even able to interact directly with the environment, it's like you write down a spell and then you execute it, it's like you speak it, and then something happens to the environment. And especially with the lower one, there's also always this implication of ethics and social aspects. So once you're able to create that, which we are currently up to, there comes power but also responsibility. So this is also always something very important to keep in mind. In the middle I put some possible applications. So usual applications in the pervasive computing field are assistance. So you would have something like ambient assisted living. So there you could classify, for instance, if a patient was falling down or something happened to the patient, and then you could react to that. Another application area is comfort, and you would have healthcare, security, safety, and many, many more applications. Okay, so this was just to give you an idea how deep learning can be applied in this area. It's not happening too much yet, and yeah, if some of you want to apply it, I'll be happy to cooperate with you on that. And I find the area very fascinating because it's directly interacting between people and computer science, so between cyber and physicality. Okay, thank you. Questions, comments?
I have a small question.
Yes.
But like smart houses are quite popular today, and people who want to live in new conditions, they already use these ideas. What's the main differences you do which had already not implemented?
So Winton left already, but we had it before also. So the the big problem today is you have specialized solutions that you can buy, and the problem is you need either time or money, because you can buy a system by a company and then it contains the parts that it contains, or it takes a lot of time because you have to build the things on your own. And the key challenge today for me is interoperability. So those systems are typically closed silos, so you can buy all components by this vendor, but if it's not offering something, then you're lost. Or if you want to integrate with some existing systems. And so what I'm working on is how can you enable via open source software, open standardization, and things like that, how can you enable that really everything that you have that can technically be controlled can also be controlled by the software? This also implies portability, so the possibility to run a software in your space and also in your space, maybe. And these are the key challenges. So that means for the systems you can buy today, if you're happy with their functionality, nothing will change. So you will have the same functionality for this specific thing afterwards. But for things you are not imagining yet, like there's Mark Weiser might be a name that is familiar to some of you. So he was in 1991 publishing a paper, and then another one in 1993 where he was talking about, okay, someone is waking up in the morning and then lots of things happen in the house. Like on the window you see the traces of people that were moving outside. So even though this might not be an application that we want to have today, one thing might be you wake up, the toaster is putting the weather information on the toast, it's heating, the coffee is starting, and all this you cannot buy today because it's just not integrated.
Thanks, but maybe it's a business problem, just how to organize this, how to integrate, how to move it together. Of course it has the scientific ideas, it should have. But maybe it's even ideal for a startup.
So indeed, it would be a good idea for a startup, but it's not only a business problem. So the scientific problem is when you come from a technical point of view, you have very heterogeneous sensors and actuators. And heterogeneity is not only vendor-driven, so that the vendor decides to do something, but it's also driven by technology. So that means if I have a battery-driven sensor and I put it to the window, it has different requirements on the communication protocols than someone I plug into the wall. And that means this heterogeneity cannot be cut with standardization because you will not have a standard for everything.
We have specific organization.
Yes?
So how is an operating system, new operating system, going to solve this problem?
How is it going to solve the problem?
How is it not? Well, maybe my question is, why are you designing a new operating system rather than using one of these systems?
So first of all, the term operating system, even though I'm using it, is somehow wrong, because an operating system is always a system that is running on one computer, or typically. So what I have is more a distributed system that you run on something. And why am I designing something new? So the thing I'm designing is running on top of operating systems that you have today. So if you download any IoT operating system, I would still run that. Why not? It's not a problem. And this one here is more a semantic operating system. And so how do I solve the problem? So in a nutshell, what I do is I say, okay, people out there are capable to write adaptation services to certain hardware, and they're able to specify an abstract representation. And what I do is I say, okay, here's an open directory where you can upload your specifications and everyone else can use it. And then people will start creating something. So you have a lamp, someone creates a model, and then this is the abstraction to the lamp. Someone else creates another model. What I do then is I say, okay, I do statistics on how are the models used. And then you have a normal evolution, like one model will be more popular than the other one. And this is then beneficial for developers of software, because when they create some sort of service, then it's more portable when it uses a more popular model. And those who do adaptation services, exactly the same happens. So my proposal there is to do some crowdsourced convergence instead of classical standardization processes, because it's faster and it's also more democratic. And the solution is that we have one crowdsourced, standardized abstraction here, and everyone is interacting only with the abstraction. And this one is breaking the direct connection between these services, doing some orchestration or reasoning, and those adapting the hardware. And so when you have different hardware in your space than I have, then you just have to run a different adaptation service because up here everything is done the same. More questions, comments? Yes.
So are there some other learning techniques, not deep learning, but some other learning techniques is like typically used in the field?
So for the model for the thing I was showing with the room, so they were using hidden Markov chains and learning with that one. So actually, I'm not aware of any paper at the moment that will use deep learning for the problems I was talking about. So, and the reason why that is the case could also be that having this abstraction as the state vectors is something that is not often done. So other groups are probably not using this technique, and then it's not so much at hand to add such learning techniques to that, because they just don't have the representation that you could feed as input to such a learning network.
I see. So it's a representation problem again.
Well. Okay, then thanks again.
Thank you.